So welcome back. Now we are going to try an actual example. No more formalism. Let's try an actual example to see how some quantum dynamics actually take place. All right, so of course we're going to pick the easiest kind of quantum dynamics is going to be with a two-level system. And our notation for this will be that the ground state we'll call G and the excited state we'll call E. And you might say, two-level system, that seems very simplistic, but at the same time, when you do spectroscopy, a lot of times you're only considering two states at a time. And in some cases, for example, with a spin 1/2 system, they're in a magnetic field, there really are only two states. So it's actually not that bad. So the way we can write this down, and you might say, well, how do I write the momentum here? Like what's p squared over 2n going to be? Right? So we don't start there. We don't start from a mechanical Hamiltonian. Of course, in our mind, we would think, okay, there's some real world problem. It's a harmonic oscillator, or it's a hydrogen atom, or a molecular orbital, and we're going to pick two of those levels. Now, how did those levels get set? Well, they got set because there really was a Hamiltonian with momentum and position and potential energy and all that. And then you figure out what those levels are. So what we're going to do is kind of take that something else was done first to determine that there were two levels. They have energies associated with them. And so we write the Hamiltonian in the basis of these two. All right, and the way we do this in the Hilbert space representation, we just write H like this. And then we have the projector onto the ground state. We'll have epsilon, my notation for this is epsilon G. Okay, and we're going to add to that the energy of the excited state. Okay, and this is our Hamiltonian for now, okay, of the two-level system with nothing else, just those two levels. And so this is giving us the energy. If you're in the ground state, this will be your energy, epsilon G. If you're in the excited state, this will be your energy, epsilon E. So we can write this as a matrix, right? So we'll write the NM matrix element, okay? Which, as you can see, is going to be picking out the G on the one side, the E on the other side, the G on one side, and the E on the other side. So in other words, N and M are indices that would go between the values of G and E, okay? And so we don't need to write down we can certainly do it. We're going to get delta functions for the different sides, right? And what we end up with, of course, is a matrix that looks like this. Then the matrix will have elements. The diagonal element, when you have G on both sides, when N and M are both equal to G, you'll have epsilon G. And when you have N and M are both equal to E, you'll have epsilon E. And if N was G and M was E, well then one of them would be 0. And make sure that everybody sees how that works. So if we go over here and we imagine calculating the GE element, so this one here, all right, so HGE will be GHE, all right, which is going to be equal to G on the left times, I'm going to run out of space, well, whatever, G epsilon G G plus E epsilon E, E, and then E on the right. So you see this ends up being 1, but this other term here ends up being 0 because they're orthogonal to each other. Same thing. All right, so this term is exactly 0. And that shouldn't be surprising. We found these eigenvectors, E and G, are those vectors that diagonalize the Hamiltonian, meaning when you write the Hamiltonian in that basis, you get a diagonal matrix. Right? I could pick another basis where the Hamiltonian will not be diagonal. For example, the symmetric combination. I could call another vector U, which would be 1 over the square root of 2 times G plus E. Okay, you can convince yourself, so that would be one vector, and then the other one would be the antisymmetric one. G minus E. Okay? Now we'll see where this comes up as the actual eigenvectors, but now it's not. So if you plug this in and write the Hamiltonian in this basis, it won't be diagonal. Okay? So what's the difference between these two? They're just rotated by 45 degrees. If this is the G direction and this is the E direction, then the plus 1, the symmetric addition of them, is a vector that points this way. So that's u. And here we have minus e, so it's a vector that points like this. It's still a perfectly valid basis, but it's not the one that is the one that gives you a diagonal Hamiltonian. Okay, so that's what we mean when we say we found this basis that makes it diagonal. Now there's not much to this, right? We have the 2 levels and we have the 2 energies, and that's not going to do very much. What we want to do now is we want to add a new ingredient to the Hamiltonian, which I will denote this way with a V. Okay, so the V is a coupling between the 2 states. That's a term that we will use for that. All right, it's a energy term that allows you to essentially mix the ground and excited states to each other, into each other. Now it's going to also turn out to have the exact form as the dipole operator, dipole moment operator. And if we think about it from a point of view of a harmonic oscillator, it will also look like a version of the position operator. Okay, only considering 2 states at a time though. All right, so we're going to call the new Hamiltonian piece H primed. Okay, and the way we make this work is we connect G. We're going to call that V there, and then E. So you see how that connects the 2. This is going to make matrix elements off the diagonal non-zero. We could have just said, well, what if we had a non-diagonal Hamiltonian? Then what would happen? That's what this is all about. All right, and then we have the E, and then we make V could potentially be complex if it was an electric field. That might have a phase. It might be a complex function just of anything. All right, and so we make sure that we have this plus the Hermitian conjugate. So we swap them and we star the operator, or if it's a simple function, which is it is here. So it would be the star. Okay, so we can express H primed in this basis. So we would have H primed NM, right? And so if we look by the same kind of manipulation that we did up here, where we found only diagonal elements, now we're going to find only off-diagonal elements. All right, so I'm not going to work through how that goes because it's exactly the same set of steps that you find here. And so this is going to be equal to, this matrix will be such that we have, so I wrote HNM equals, what I really mean is H is equal to this. All right, so H primed is represented by this matrix 0, and then V, and then V star, and then 0. Okay, the off-diagonal elements are responsible, if you think about it, for coupling these 2 states. So there's a classical analogy to this. If I have one pendulum over here, another pendulum over here, and I connect them, for example, by a spring, then I have one oscillator on this side with its displacement, another oscillator on this side with its displacement, but because of the spring, the force constant of this pendulum will depend on the displacement of this pendulum from its equilibrium. And that's going to give it a coupling. Now turns out this will be exactly like the kind of coupling that you have in molecular vibrations. It's similar to the coupling that you have in spins. It's also similar to the coupling that you have with multiple electronic systems. So this picture here is going to come back over and over and over again. We're starting out now with just 2 states, but later on we'll pick 2 sets of states, and then we'll be able to do coupling between those. Okay, so let's take a look at this. Now we have the whole Hamiltonian together. So H is going to be the Hamiltonian for the diagonal, meaning the field-free case, the case with no V, and then the one when we add the potential. All right, so that's going to be epsilon G, epsilon E, V, and V star. Okay, and remember that the basis we've chosen is the GE basis. So this is a 2 by 2, so let's make sure that we're very concrete about this. This will come back later. All right, so what we mean then is the basis G, for example, is going to be 1, 0, sort of like the I-hat in a 2-dimensional system. E will be 0, 1. And you can convince yourself they're orthogonal. If you take the scalar product, you get 0. They both have a unit length, which you calculate using the Pythagorean theorem. Square the elements and add them and take the square root, then that's equal to 1. Okay, so now what we're going to do is consider how to figure out the key things that we want. We always want the same thing. We want the eigenvalues and the eigenvectors. Now it turns out for 2 by 2, it's very easy to solve this by hand. And once you've seen it done once, In some sense, you don't ever need to do it again, but it's good to see it done once. So let's do it the slowest possible way. So you do it by solving this kind of equation, right, which is, and I'm not going to derive the theory of the linear algebra. I'm going to use the linear algebra results as they are, but I'm going to walk through how you solve the eigenvalues and then insert them to get eigenvectors. But I'm not going to describe why, for example, you need to solve this equation. All right, so the standard way to find the eigenvalues is you set up this determinantal equation, which is to say you take the determinant of the matrix you have minus lambda, which is going to ultimately be a polynomial whose roots are the eigenvalues, times I, which is the identity operator, and set that equal to 0. Okay, so that looks like this. H is this matrix here. Epsilon g minus lambda times I means you'll have a minus lambda here. Epsilon g minus lambda here, and V star. And the bars mean take the determinant. All right, so for a 2 by 2 matrix, the determinant's very easy. It's this times this minus that times that. So we write that down. Epsilon g minus lambda times epsilon e minus lambda minus V times V star is equal to 0. All right, now V times V star, we know, is the modulus squared of V. And if V was a real number, then of course that would just be V squared. So that's no big deal. But I'll leave the bars there just to remind ourselves that the V can have complex contribution to it. All right, so when we work this out, we write down, we expand out this product here, and we'll get epsilon g, epsilon e from these two, minus lambda epsilon g, minus lambda epsilon e, plus lambda squared, minus v squared equals 0. Okay, so that's that. Now all we have to do is group the terms. Our variable is lambda, so think of that like as x or whatever. And we have lambda by itself. Let's put that up here. So we'll have lambda squared. There's lambda squared. Then we have minus lambda times, so we have epsilon g plus epsilon e times lambda. All right, good. And then plus epsilon e epsilon g, or epsilon g epsilon e, whatever. All right, and then minus v squared. And that's equal to 0. So if you look at this like in a quadratic formula, this a is 1, b is negative, that's sum of those two things, and c is all the stuff that's left over here. All right, so you know how to do the quadratic formula. So we put this into the quadratic formula, you get two roots. All right, I'll call one lambda minus, and it's because of the plus minus in the quadratic formula. So it's equal to 1/2, that's 1 over 2 a, I guess. And then we have the term out front, so epsilon e plus epsilon g minus, and then the big square root that you know is coming. We'll make some simplifications of this, and you end up with expanding out the term. Yeah. What happened? Oh yeah, just plugging it in with the b squared minus 4ac, and so you end up with epsilon e squared minus 2 epsilon e epsilon g plus epsilon g squared plus 4 v squared. Okay, so when we summarize this term here can be rewritten as a square of a difference of two things. So this is equal to epsilon e minus epsilon g squared. Of course, you could switch the order of these if you like. I write it this way because it's common to quote the energy gap between the two states. And usually we like energy gap to be the greater one minus the smaller one, so you get a positive number. So we're going to call this here delta. Okay? And then all of that stuff is multiplied by 1/2. The lambda plus looks exactly the same, except there's a plus sign here. So you have epsilon e plus epsilon g plus the square root term. Now we can put in our simplified version. So delta squared minus 4v squared. All right. And so what we can do is we can look at the difference between the two states. So what we have is this state here, and then it's going to be split, or it's going to be changed into two new states with different energy. So for example, if we calculate lambda plus, the one with the plus value, and these are now all real numbers, so there's no worry that the energy somehow got complex, right? That tells us about the relationship between these two things. Lambda plus is there's a plus sign here, of course. Otherwise, there's no question this could be negative, and that would be very bad. So lambda plus minus lambda minus. All right, when you do that, the stuff out front goes away. All right, and you end up with 1/2. You just have the square roots. So 1/2 of the lambda plus 1. So it's the delta squared plus 4v squared, right? And then minus minus, so plus 1/2 of the same thing. Delta squared plus 4v squared. So that just ends up giving us this thing that's in the square root. Delta squared plus 4v squared. All right, and so this is the gap, the new energy gap, the energy difference between the ground state and the excited state for the new coupled system. Now let's just make sure that this makes sense. If I turn off the coupling, in other words, if I set now back v equals 0, what do I get? Well, this term will go away, and I'll get lambda plus minus lambda minus is equal to the square root of delta squared, so that's equal to delta. All right, where delta was just the difference in energies without the v. So that shows that we get right back to the problem that we started with, then when there was no coupling at all. Okay, so what you notice is that the energy difference between the two of them is proportional to both the energy gap and to the coupling. What is that? Why is that important? That's important. Energy gap meaning the gap without the coupling, delta. That's very important because what it tells you is if you have two states in any kind of spectroscopy you do, all right, you don't know if the two states you have the difference in energy levels because of the energies that they had without the coupling being different, delta, or a very large coupling and the energies could in fact be the same. And of course, it could be anything between those two cases. So that's a big problem. We often don't know the difference between what we might call the site energies and the couplings because they both enter in making the eigenvalues. That will affect other things like selection rules and transition moments and stuff like that, which it absolutely will do. But if you just have one transition, it's hard to tell where it came from. That's one of the reasons why people do high order spectroscopy. Now, what if we set the two states to be degenerate at the beginning? All right, so we set those two states to have the same energy. That's fine. There's no reason that these couldn't be different, or the same, sorry. Then that sets delta equal to 0. All right, so if we set delta equal to 0, we have two states. They couple by somehow their mutual interaction with each other, or something field that's connecting these two states together. And now what happens is we look at what is the energy gap. So if delta is equal to 0, the energy gap is the square root of 4v squared. All right, well, obviously that simplifies a lot to just 2v. All right, so that's the energy gap. And what that means is that the lower energy state will go down by one amount of v. Whoops, I drew too many lines. One amount of v, and the other one's going to go up by an amount that's exactly v. Okay, so what that means is if you had some intuition about why two states that were coupled to each other, for example, would be the same, like two identical spins or two identical carbonyl vibrations or two identical electronic states, and then they couple and they split, then looking just at the difference between those two transitions will immediately tell you what the coupling is, right? Let me make sure that's very clear. So right now, it's not obvious probably how we're going to use this model of two levels because it seems like these are the only two levels. But what we can do, as what we'll find out later, is that if we have a system of coupled two-level systems, multiple ones, we can actually consider the first excited states using this exact model here. So if I have two-level systems like this, then there's a ground state here, and they're coupled to each other, what's going to happen, this is just like previews of coming attractions, is that one state will go down energy, one state will go up in energy, and then you'll have the energy, there's a state that corresponds to two excitations, this one and this one, that'll be up higher level up here. All right, so you end up with 4 states. In a lot of spectroscopy, you can't see this, or it's very weak, or you're not interested in that. You're only interested in these two. Well, this splitting here is going to be 2V as well. All right. So if I look at a vibration, for example, or some other system that has 2 states that are coupled together, it's very common to see something that looks like this. All right. And this splitting here, at least within this very simplistic model, will be 2V. Okay. You can also think of it like the difference in energy between, for example, if you have a 1s orbital on a molecule and a 1s orbital, as the difference between the energy of the 1s orbital and the 1s star antibonding orbital. Right? That'll also be 2V, and V is the coupling that is caused by the electron overlap, the wave function overlap of the 2 atoms. Okay, so these ideas are extremely generic. I'm just doing it here for a 2-level system, but this will come back over and over and over again. And it also highlights one of the sort of features and maybe annoyances of the way we use this whole language to talk about coupling. Because once the system is coupled, you don't need to call it that anymore. You can just say it's the system that happens to be described in this way as a Hamiltonian that's different from the one you started with. But it looks like, or acts as if it was a system that you started with a coupling between the 2 of them. In other words, let's say you lived in a universe where there weren't any individual parabolas. There weren't any individual pendula. All right. Well, then talking about 2 coupled pendula wouldn't make any sense. But talking about this thing, whatever that is in that world, right, the doodad, it's totally normal. So you would think of everything in terms of this. And if someone said, oh, there's 1 pendulum, or 2 independent pendulums. It's like, whoa, what do I do? I can make a linear combination of 2 different modes of my coupled, of what we call coupled, of this doodad here, and that can get me back to a localized mode on one side and a localized vibration on the other. All right, so it's really all about the basis that you choose, and sometimes the basis has intuition, and sometimes it gets in the way. All right, so in NMR, of course, this splitting can be the energy levels of the excited states can be controlled by a magnetic field, all right? And so that's going to influence how you actually see the different vibrations. In electronic spectroscopy, the energy levels of the states can be controlled, not so easily controlled necessarily, but they're influenced by the environment, or if you make chemical substitutions, and a similar effect happens in vibrational spectroscopy. So these ideas you'll see are quite generic. So this is just the Hamiltonian that we get when we have coupling between the 2 states. So what we've done here is we've solved the eigenvalues. That's actually not so bad, right? We have the energy levels. What we need to do next is we need to figure out what the eigenvectors are. So we're going to work out how to do the eigenvectors. And then what we're going to do is we're going to pick a system, like a realization of the system, and compute the time evolution of this system. It's going to be sort of like asking, when we have the system evolving, what's the probability we find it going from the ground state to the excited state of the uncoupled system with the coupling, right? So you might say, well, how do you even have no coupling? Like, how do you have the uncoupled system to begin with? So that's leading us towards thinking about the idea that when we do spectroscopy, the molecules are just sitting around, they have these energy levels in them, then we interact with them with light, and at the end of our interaction with the light, the system state will be changed. All right, so we're asking the same kind of questions about what's the probability of making a transition from one state to the other of the field-free system states when we interact it with the field that we can turn on and turn off.